So I would like to shout loud enough to reach Mohab and thank him personally for inviting me to my home university. I grew up here. So it's very special for me to lecture here in this university. Also, the other very special thing is that the average age of this crowd is amazingly low, which is very special for the Poema Network. It's really nice to lecture to young people. And I'm very happy to, I hate acronyms. I never understand acronyms. I don't understand what acronyms are good for, because you say the acronym and then at the end you explain to people what it means. So I went to refresh my memory about where the acronym POEMA is from. So polynomial optimization through efficiency, moments, and algebra. And I tried to pick out of these 1, 2, 3, 4, 5 keywords, a keyword to lecture on, and I think M is moments. And we know that it was a fundamental tool in the development of the polynomial optimization approach that has been promoted by the Lasserre moment SOS approach. And in that approach, the truncated moment problem has played a fundamental role. So I would like now to talk about the generalized truncated moment problem. And I forgot that today is September 6th. So sorry, I wrote September 5. Okay. So this is a report on a paper that we just got accepted in the Journal of Operator Theory. It's a very, very long paper. It's the longest paper that I ever got accepted. There are areas in the paper that I don't know well at all, because my co-authors wrote those areas of the paper. So those points I will just indicate what they are about, and I will not try to cover them. But the title of the paper is The Truncated Moment Problem for Unital Commutative R Algebras, and that is really sounds extremely abstract. I will try throughout the talk to indicate what is the motivation behind looking at such an abstract and general setting. I would also like to say that the paper is dedicated to the memory of Murray Marshall, because we actually started discussing this in 2012, 10 years ago with him, before he passed away in 2015. So that being said, I would like first, in a nutshell, to make sure that I pass the message in a compact form. I had prepared a 45 minutes talk. I thought this is the time I'm given, but now I have more time, so I have time for jokes and for relaxation. So I would like to give in a nutshell first some background about the finite dimensional KB truncated moment problem on A. So it's a lot, I mean, all the parameters that I will need in the talk are really appearing in the title. So who is who, I would like to say? Well, in the finite dimensional case that I'm talking about as a state of the art, A is the algebra of polynomials in n variables. K is a closed subset of Euclidean space R to the n. B is the linear subspace of polynomials bounded in degree by D, D being a natural number. And this is the context that the problem was studied by Courtauld and Fialkov and many other people, but obviously I am here somewhat biased since Courtauld is a co-author on that paper, so I will not try to give an exhaustive list of all people who worked on this. There was a slight generalization, an interesting generalization, mainly due to knee, but it was applied, this approach of knee was applied, as far as I am aware, by Poutinat and also by Monique and Bernard, to special cases of the truncated moment problem, kind of sparse cases or so on. So let me explain what this is about. What are the parameters here? Rather, I'm just giving you the parameters right now. I didn't say what the problem is yet, but the parameters play an important role. So the parameters here are again that A is the algebra of polynomials in finitely many variables. K is a closed subset of Euclidean space Rn, and this time curly A is a finite set of monomials, and the linear subspace B that we are looking at is simply the subspace generated by A. So that would be the context in which Ni looked at this A truncated moment problem that I will formulate in a moment. It's a bit more general than the previous one that is called the classical finite dimensional K moment problem. So the generalized KB truncated moment problem on A now is what are the parameters that I want to look at instead. And this is our contribution in this paper, and has been my contribution in the last 10 years or so to the moment problem, to get out of the finite dimensional setting and go in a non-necessarily finite dimensional setting. And I will try to advocate why this is more than just abstract algebra, but really interesting. So A is now a commutative unital algebra. K will be a closed subset of the character space of A. In a moment, I will explain what the character space of A is. And B is a linear subspace of A. These will be the parameters in this general case. And let me say why we are interested in this general case, why it takes us away from the constraints of finite dimensionality, because here A can be any real algebra. It can be not finitely generated, for example, and typically when it is not finitely generated, in most natural contexts where applications of the moment problem occur, the corresponding character space is not a finite dimensional real vector space, but rather an infinite dimensional real vector space. And this occurs in nature when we look at applications. In particular, Maria Infusino is a specialist in this approach because she works a lot with collaborators in quantum chemistry and statistical physics, where the realizability problem in statistical physics demands an infinite dimensional setting, and the representability problem in quantum chemistry also demands an infinite dimensional setting, and those people are lost because they don't have the mass that they need for it. So this is our strong motivation. I'm a little bit cheating and citing from my talk from yesterday. Forgive me for that. I gave a talk yesterday. Okay, so I want to say that in this paper, in the part of the paper in which I actively collaborated, there are three main theorems that we prove. These three theorems are a solution to the generalized KB truncated moment problem that I will formulate in a moment. And they vary in assumptions. And that is kind of annoying, but it's not too annoying because it turns out that these assumptions, when you come to applications, do appear naturally in the targeted problems. So the first theorem that I will present is under the assumption that the algebra is a topological algebra. The topology really is a tool that helps. We will first assume that A is endowed with a seminorm, and I will explain in a moment what a seminorm is. And in fact, more generally, that A is endowed with a locally convex multiplicative topology. These are topologies that are induced more generally by families of seminorms. So that will be the first theorem. And that first theorem is the backbone for the two other main theorems. The second one, here we will no longer assume that there is a topology prescribed on A, but instead we will make an assumption on K, on the set K that we are looking at, and this is the compactness. And you will see that from the compactness, we will just create an appropriate topology, an appropriate seminorm to work with. And then starts appearing conditions on B that are in theorem 2 not yet too annoying. And it's also the backbone for the theorem 3, where the assumptions, the parameters are as follow. Again, A is arbitrary. I mean, not arbitrary, it's a commutative unitary algebra, of course. K is arbitrary. We don't assume anymore that K is compact, but the price to pay are more bizarre conditions on B. And we struggled with those conditions. I will show them to you in a moment, but actually convince ourselves that they are all necessary. The theorem doesn't go without. We have counterexamples if one drops any of the conditions that will appear. So this is what I want to say in the first 3 parts of my talk. And then in the last part, I want to talk about application. The paper is full of applications. I want to highlight here in this talk one application, which is in a sense not super exciting, but enlightening, because I want to show how we retrieve the finite dimensional K truncated moment problem from the general theorems that we will give. There are other applications to the truncated moment problem for point processes. This is a typical application where the infinite dimensionality is requested. There are applications for the triangular, rectangular, sparse truncated moment problem that I mentioned a few minutes ago. There are connections to a problem called the subnormal completion problem, and there is version of Haviland and so on. But these things in orange, I will not talk about today. Yeah.
So is there a natural example of like this generalized context, or just a case where you say you can do this for this in any unit of algorithm? Is there an actual example that you can think of?
Yeah. The algebra of polynomial in countably many variables.
I see.
Countably infinite. Sorry?
So I mean, usually we think of algebra polynomial with finitely many variables, but countably many variables.
Yeah.
Is the motivation.
That's, well, yeah, this special one deserved a paper on its own, just that one. But of course, it could also be algebras with relations. I mean, here it's freely generated, but there could be relations that would complicate matters. And so it's completely general. The other interesting algebra to think about is the symmetric algebra, the symmetric tensor algebra. That is also a very interesting case. So let me then start by telling you what is the classical truncated moment problem. So again, we are considering the polynomial ring of real polynomials in finitely many variables, and K a closed subset of Rn, and B a linear subspace. Linear subspace, that is the point. It is not, B is not necessarily a subalgebra, it's just a linear subspace. And now here is the problem that we are looking at. We are looking at a linear functional that is defined solely on B, and we will call this linear functional K positive if it takes non-negative values for all polynomials in its domain of definition, which themselves are non-negative on K. This is the typical positivity condition that occurs in the moment problem. For a set of polynomials A contained in Rx and a K positive linear functional L on A, the A truncated K moment problem, a lot of words to say, is the question of establishing whether such an L, such meaning a K positive L, can be represented as an integral with respect to a positive radon measure whose support is contained in K. Here, positive radon measure on R to the N, whose support, the support of the measure, should be contained in the prescribed closed set K. In the case where A happens to be the set of all monomials of bounded degree for some natural number degree D, the A truncated moment problem is known as the classical truncated moment problem. For the case where A happens to be the set of all monomials without bounds on the degree, this is the classical full K moment problem. I have been working on the classical and also generalized full K moment problem for the last 10 years. And this is the first time with the encounter of Courtauld that I turn my attention to the truncated case. So this is the classical truncated moment problem. And there were answers. I want to highlight here two typical answers that appeared in their work of Courtauld and Fialco, and again, work of others, many others that I'm not citing here. And there are many theorems and many results, but I just chose to highlight those two in that talk. The first theorem is for the case when K is compact. And the theorem says that if the prescribed support of the measure is not only closed, but also bounded, compact, and the span of A, that subspace, the span of this set of monomial, contains a polynomial strictly positive on K, then any K positive linear functional L defined on that linear subspace is K representable by a measure. In fact, the other direction is also true, but it's kind of the trivial direction. So this is an if and only if statement, and that appears in that one paper of Courtauld and Fialco, of which I can give the reference upon request. So that is the case when the prescribed support is compact. More generally, the general case is this, what they called flat extension theorem. And it is the following: when you consider the space of polynomials of bounded degree bounded by 2D or by 2D plus 1. And the result is the following. If B is the space of polynomials bounded in degree by 2D or by 2D plus 1, then a K positive linear functional L defined on B is K representable by a positive radon measure supported on K, if and only if L admits a K positive linear functional extension to that bigger linear subspace of polynomials bounded by 2D, of degree bounded by 2D plus 2. So they reduce the answer of the moment problem is reduced to a question of extension, being able to positively extend to a larger space, larger still finite dimensional space, a linear functional that was already positive. The way it is stated, this theorem. So the general truncated moment problem now is the following context. Now A is a commutative unital R algebra, and chi of A, what I called before the character space, it is the set of all real valued R algebra homomorphisms on A. Okay, so it is the set of all alpha that go from A to R and is identity on the real scalars and is multiplicative and additive. It's an algebra homomorphism. So, I mean, really, these are maps from A to R, simply maps from A to R, not simply, of course, they are homomorphism. Consider chi of A as a subset of the Cartesian power R to the A. Now, the Cartesian power R to the A is a real vector space of possibly infinite dimension. And that is going to be interesting in a moment because we will endow that set of characters, we will endow it with a topology that will play a role, because we need a notion of Borel sets in order to talk about measures on this character space, right? So we need a topology that I will explain in a moment. But before that, let us mimic what are polynomials, because here this is not an algebra of polynomials, this is an algebra, but we can mimic polynomials by the so-called Gelfand transform. The Gelfand transform of an algebra element is a map, a hat, that goes from the set of characters into the real, so it's real valued maps. And they are defined by duality. They are defined by a hat of alpha is alpha of A. Now, alpha, chi of A is endowed with the weakest topology, which will make all these maps a hat continuous. This topology coincides with the subspace topology on chi of A, which is inherited from the product topology on R to the power A. There is that annoying thing. What is it blocking the view? The corner? No. Okay. Also, for the purpose of our work, we will always assume that chi of A is non-empty. We were a little bit taken aback when we realized that sometimes we were, without noticing, heard that there was a thesis defense here just before my own thesis defense here in Jussieu. And the person kept talking and giving properties and properties of the object that the PhD student found, and talking and talking. And then someone in the examination asked, can you give an example of such an object? And it turned out to be the empty set, what he was talking about. So we realized that the character space of an algebra can be the empty set. And so we will assume that this is not the case here. So the algebras we are, yeah?
There any topology on A?
For now, not yet. But as I said, in the first of the three theorems that I want to talk about today, I will assume that there is a locally convex multiplicative topology on A, which is a topology coming from a family of seminorms. boundedness in that case. It's a special case, yeah.
So for your motivating example of following algebra count the many variables, what are the characters? Are they just point evaluations of points this finitely many non-zero coordinates?
Yeah. So for that case, for sure, the character space is non-empty, but you can twist that example badly, right? So you can, for example, divide by the ideal generated by 1 plus xi squared for all I, and then the character space becomes empty, right? Because there is no solution for that. So when it's freely generated, it's point evaluations indeed, and then we have peace of mind, the character space is non-empty. Yeah?
Was this thesis defense successful?
Sorry?
Was the thesis defense successful?
Well, I wasn't revealed the truth. I think it was my doctor supervisor who gave me this as a warning before my own thesis defense. So. Okay, are there any more questions about this slide? Because I have time. Nice. Okay, so the last thing I want to still in the abstract context define here is for any subset S of the algebra, we will define the non-negativity set like the semi-algebraic set K sub S to be all characters such that alpha of S is mapped into the positive half line. So all characters that are non-negative on S. I want to relate this to the finite dimensional case that we were talking about at the very beginning, and it's a very quick observation. Actually, Greg said it for the algebra infinitely generated, generated by countably many variables, freely generated by countably many variables, but it's also true, of course, in the finitely many variable case, because what is a character? A character is a homomorphism from the polynomial algebra in finitely many variables to the reals. But if you think about it for a moment, now after 4 years of working in Kuhlmann network, you will realize that once that you prescribe to the variables x1 to xn a tuple, you assign to them a value, a tuple a1 to an, a point in Rn, then the homomorphism is completely determined, right? Because you will just substitute whenever you find a monomial in your polynomial, you will substitute for this. Therefore, in that case, the character space, every character just corresponds to a point, and the character space is just identified with Rn. So we are really back in the classical situation in that case. Also, because here we have a base field is an infinite field of characteristic 0, we also have that whether a polynomial function or a polynomial as a formal object are the same, right? So we don't need this Gelfand transform decoration. P hat is P. And finally, when you look at this non-negativity set, you just get the semi-algebraic set in the classical sense. So we have peace of mind. This generality doesn't lose what we know already. Now I want to formulate finally the main object of this talk, and that is this generalized truncated K-moment problem. So let A be a unital or algebra, K the subset of the character space enclosed. We have a topology now, so we can say closed. B a linear subspace of the algebra, any linear subspace, and L a linear functional defined on B. And the B K truncated moment problem in this general context asks whether there exists a positive radon measure nu on the character space whose support is contained in K and such that mu represent L via integration of the Gelfand transforms. So it's the exact analogous of the previous question, but tailored to this context. Yeah.
May I ask something? So you mentioned the topology on the XA, on the character and K. So what is it exactly? Is it the same? Well, it's not the same as in the example.
It is.
Well,
It is. So it is the weak. You can define it two ways. You can define it to be the weakest topology for which all the A hats, the Gelfand transforms, are continuous. But you can also go another way. You can say, okay, chi of A is naturally embedded, even as a set, in R to the A. And R to the A has a product topology on it. So it goes down to subspace topology. This is the topology on chi of A. Okay, so now comes the case someone asked before, is there a topology on A? Now is the first case that we consider, and when there is a submultiplicative semi-norm prescribed on A. So a submultiplicative semi-norm is a function from A in the positive reals such that, first of all, it respects scalars modulo putting absolute value. So a rho of R times A is equal absolute value of R times rho of A for any A in A and a real number R. It is subadditive, meaning that rho of A plus B is less than or equal than rho of A plus rho of B. And it is submultiplicative, meaning that rho of AB is less than or equal than rho of A times rho of B. I want to define here the Gelfand spectrum of a semi-norm because it will be related, you will see in a moment, to localizing the support of the measures that we are talking about in this context. The Gelfand spectrum of the semi-normed algebra A rho is the set of all characters that are bounded, all bounded characters. So such that the absolute value of alpha of A is bounded by rho of A for all A in A. The Gelfand spectrum is compact because it's basically contained in the product of the intervals minus rho of A plus rho of A, product of all these. It is a closed subset of a bounded set, so it is compact. And that's where the interest for the support comes. And a last thing I want to define before formulating the theorem is that let C be a cone in A. For example, we will consider the case where C is a quadratic module, or actually a 2D higher order modules we have also considered, but for simplicity, I'm not mentioning this here. And for any A in A, we will define the norm of A with respect to the cone and with respect to the prescribed semi-norm to be the infimum over P in C of rho of A plus B. And with these objects, I can formulate the theorem. And the theorem says, let A rho be a semi-normed algebra, B a linear subspace, S a quadratic module, and L a linear functional on B. Then L admits an integral representation with respect to a positive radon measure whose support is contained in the Gelfand spectrum intersected with the semi-algebraic set. So here you see that the support will be compact, right? If and only if there is a natural constant, a real constant, positive real constant G, such that L is bounded in absolute value by G times this norm of S and rho. Now, the proof is almost entirely based on corollary 3.8 of our work with Gassemi and Marshall that appeared in the Journal of Function Analysis in 2000, 14, I think, which is called Applications of the Archimedean Positive Tensatz. I mean, Mary Marshall liked to call the Archimedean Positive Tensatz Jacobi's representation theorem. That's why it's called. And we could export the elements and the ideas to adapt it here to the truncated moment problem. I should say that this theorem is actually more general. We can also express it for A endowed with a locally multiplicative convex topology. These are topologies that the neighborhoods are just finite intersections of neighborhoods of finitely many seminorms. And then you can pick up one and do the trick. So this theorem is also true for a locally multiplicatively convex topology. So this is step one of the story. Yeah.
So this is row again. Going back to your example, what is the example of the seminorm again? Like in the usual truncated moment problem, or in the or counting any variables. Where does this flow come?
Where does it come?
I just want to understand. Can you give me an example of such a seminorm? That's what I'm.
Okay, that's like the thing that my PhD advisor warned me of. Okay. An example of a semi-normed algebra is a Banach algebra, for example. You want an example of a semi-normed algebra?
I just want to understand how this would apply in the, if I just do the regular polynomials.
L1 norms, LP norms, L1 norms on coefficients, for example.
Okay.
This is a very, we worked out these examples in details, because when you look at these and then you look at the Gelfand spectrum, you get very nice geometric objects. There was also work by Jean-Bernard Lasserre and Tim Netzer, where they used the LP norms for their investigation. Does that answer your question?
Yeah.
At least it's not the empty set.
And the infinity norm?
L infinity norm, of course. L1, L infinity, LP, LQ, all these things. And there are also those more generally weighted LP norms. Yeah, and these are also give very beautiful results. So all this is in, well, applications of this is in these papers with Marshall. God bless his family. The second theorem is, now we start assuming things. We assume that the support is compact. Let A be in commutative unity algebra, K compact, B a linear subspace, such that there exists an element in B so that the Gelfand transform is strictly positive on K. So, I mean, that appeared before in the theorem I cited in the classical case from Curto and Fialco, but here it's the general context. Then every K positive linear function in L admits an integral representation by a positive Radon measure supported in K. It's the exact analog of the finite dimensional case that I cited from Curto and Fialco. So the proofs are very technical, but I try to give an idea in a nutshell here. So you apply theorem one. Theorem one was the one where you assume a semi-norm on it by exploiting actually the compactness of K, because if you have a compact set, then you have a norm. And it is the one that is called the rho K here, which is the supremum norm on the compact set. But then it is actually a norm on a bigger algebra, which is the algebra of continuous real valued functions on algebra, there is a linear functional and there is the linear subspace. And so you bring yourself into this situation by considering the algebra of continuous real valued functions on the topological space K, equipped with the semi-norm that is the supremum norm, and the L that you consider is a bounded extension of your original L, and here there is some quite brutal use of something called Choquet's lemma. Okay, it's from function analysis. Okay, and then the third theorem, theorem 3, is the following. Let A be a commutative unital R algebra. Now I will not assume compact anymore on K. K is a closed subset and B is a linear subspace. But now the price to pay is very annoying assumptions on B. They really look like nothing that I can make friends with, really. Such that there is a P in A, but not in B. So it should be in the difference, A minus B, which is the Gelfand transform of P is greater or equal to 1 on K. The linear subspace generated by my original space B and that new element P contains 1. This linear subspace generates the algebra A as an algebra, and the supremum over alpha in K of the absolute value of the quotient B hat alpha over P hat alpha is finite for all B in B. Okay, so these are the conditions on B. Now let L be a K positive linear functional. If L has a K positive extension to BP, so BP is the original space B, and then you take an extra generator, that's miraculous polynomial P, then there exists a K representing measure for L as we want. So there is a solution to the generalized moment problem. And as I told you, I was really rebelling against those conditions. I was annoying my co-authors so much that they produced a counterexample for anyone if you drop any one of these conditions. There are counterexamples in the paper. Okay, so now I want to come back to the applications to the classical truncated moment problem. And there is a little lemma that says the following. For any monomial of degree 2D or degree 2D plus 1, here we are back in the polynomial algebra, right? Because I said application to classical. So we're back in the polynomial algebra, infinitely many variables, the usual polynomial algebra. For any monomial of degree 2D or 2D plus 1, there exists a polynomial P of degree at most 2D plus 2, such that the monomial in absolute value is bounded by P of X, and P is greater or equal to 1. So this is actually the main thing here is a use of the arithmetic geometric inequality. So again, I put the proof in a nutshell here. So the idea is that you look at your monomial and you split it into the even part of the monomial. So you rewrite the tuple alpha as gamma plus 2 beta, where gamma is a tuple of 0 and 1s, and the rest is twice beta, right? So you can rewrite your monomial as the product x to the gamma times x to the 2 beta, and there are two cases to consider. Maybe this gamma is entirely 0, so this doesn't appear. Is there any question? No? Okay, in that case, you set P to be the product of 1 plus xi squared for every variable xi to the beta I. And in the other case, that's where so this one you don't really need to argue with geometric that you want. So here this lemma is useful because it will give us the P, the mysterious P that is so annoying in that theorem 3, right? So let's look what this corollary is saying. So it's saying, let P be what? Okay. Let P be a set of polynomials of bounded degree K. Then there exists a polynomial of bounded degree K plus 1, I mean bounded by K plus 1 if K is odd, or bounded by K plus 2 if K is even, which is greater or equal to 1, and this polynomial satisfy exactly the condition that appears that we want from the P, right? So how do you concact this polynomial? I mean, you just list the idea of the proof is you list the monomials, and there are only finitely many. The basis of monomials is finite. So you go and get one of those using the previous lemma for any one of those monomials. So luckily we have only finitely many, then we can take the product of finitely many polynomials, and that will do it. And finally, the corollary to the theorem 3 now that I had using that small observation is indeed let K be closed. So I am back in the classical case. K is closed, L is K positive on polynomials of degree bounded by 2D or by 2D plus 1. Then there is the P that we want. There is a polynomial of bounded degree 2D plus 2, which is greater or equal to 1 and satisfies this soup of f of x divided by p of x is less than infinity for all f in my linear subspace Rx to d, respectively Rx to d plus 1. Thus, L, now applying our theorem 3, has a representing measure if and only if L admits a k positive extension to BP, right? So let's compare this to Kurtoff-Fialkov, what is it called? Flat extension. And this corollary slightly improves the result of Kurtoff-Fialkov because it requires the k-positivity extension to a subspace BP of Rx2D plus 2, right? Which is potentially maybe much smaller even than the whole thing, right? So that is corollary to theorem 3. And the corollary to theorem 2, I already indicated, is immediate. So in the compact case, what we get from theorem 2 is the classical result that let K be compact and be a subspace of Rx to D. Then there is such that there is a P in B which is strictly positive on K. Then any K positive linear function admits a representing measure. Thank you.
Any question, comment, remark? Please.
I thank you. I really like to talk a lot.
Thank you.
Since we were talking about the conditions in theorem 3, and that you asked your co-authors a lot
are really simple.
Okay.
They're annoyingly simple, but I didn't gain intuition.
Okay.
So you can, I mean, the paper is on the archive too. I could give the examples here if anyone
For
wants.
example, the first one, does it look like looks a bit like Ambara?
The first what?
Yeah.
Oh yeah, the first one. Maybe the first one could be have a natural feeling to it. Yeah, maybe. Yeah.
The last one, does it state something like boundlessness or?
Yeah, so I think that the things that personally annoy me is this thing that BP has to generate A and one has to be contained in the subspace. The boundedness is to be expected, I think, more than anything else. But as I said, the examples are very simple. So even in one variable.
So here you use this K positivity, which may be, say, difficult to manage in practice. So if there are, what's happening if you relax this condition?
Oh, okay.
Saying it's
Yeah.
positive on the square.
On the pre-ordering.
On the,
Yeah, or on the quadratic model. Very natural question. Don't think that we exploited this aspect. That is exploited a lot in the full Roman problem. But yeah, I mean, it could be exploited in all the cases where we know that K positivity is the same thing as being in the quadratic module. But I'm not sure whether it works for subspaces, does it? This,
well,
I'm not sure. That's
could be interesting.
that's
to have.
something interesting to look at. Yeah, thank you for the question. I mean, there isn't the Archimedean Positivstellensatz on a subspace. Not really, because you have to look at the quadratic module in the subspace. I don't know what happens there. Maybe someone else knows. I don't know. Haven't thought about it.
So I have also maybe a curiosity. So your K is always closed, sometimes was compact, no? So a natural question in if it is convex, make life easier, simplify something is meaningful, or
So I will actually answer not your question. I know it's very bad style, but I would rather tell you that when we work with those weighted semi-norms, it always happens that the support of the measure turns out to be convex.
okay.
So it looks like a very natural situation. I'm not sure it's reversible. Yeah, perhaps if you start with a convex compact support, you can retrieve from this situation already an interesting submultiplicative seminorm.
Other question? So if not the case, we thank and